Swayam Prabha. Digital India. Educated India.
So, in this lecture, we will discuss about constraint MD simulation. Before we discuss the principle of constraint dynamics, let us recap what we have done so far. What we have learned so far is that if I have a system of n particles and if I know the potential energy that is U of Rij, then we can set up the equation of motion, which is basically Newton's second law, where this force here is obtained by taking the derivative of this potential energy. So, we have potential energy, then we have the equation of motion, then we also looked at some algorithms by which we can update positions and velocity of each particles. For example, if you recall the Verlet algorithm, where the particle position is updated in time using the current position and the pole position and the acceleration. So, this we have done, and now if you want to go from let us say from atomistic system to a molecular system, and you may recall that molecules are basically made up of multiple atoms connected by bonds, and then there is also bond angle between these, and there is also torsion. So, then we write the total potential into sum of intermolecular potential and intramolecular potentials. In the intramolecular potential, that is the potential energy between the atoms within the molecule, there are various forms. For example, you can think of this bond potential, which could be written in terms of some harmonic function, where this Kb here is the strength of the bond and the L naught here is the equilibrium length of the bond. Anytime the bond length varies from L0, there is a penalty, so it has a harmonic form. Similarly, if you have the angle bending, you can have the potential energy for angle bending in a very similar fashion, where there is a equilibrium angle between two bonds, and that is theta naught. Anytime this angle between the two bonds, when it varies from the equilibrium angle, then there is a penalty for the angle bending. And then you can also go on beyond asking the torsional potential as well. If you recollect, we have written something like and so we have done these kind of models for intramolecular potentials. So, now when you want to simulate a system of molecules apart from intermolecular interactions like Lennard-Jones or Coulombic interactions, you can also include this intramolecular interactions via these additional forces, and all this can be used in describing the total potential energy, and we can again use the calculation of force on each molecule and then update the position velocity of each atoms in each molecule. So, in principle, whatever we have done before for atomistic system can be very readily be applied for molecules also. So, this is a normal way of doing simulations. However, it turns out that when you look at a molecular system, the time scale with which certain process happen are not of the same order of they are not of the same order. For example, if you look at this bond vibration, these are high frequency vibration which happens at a very small time scales. Whereas, if you look at the translational motion or rotation of these molecules in time, they are much slower process. So, if you adopt a MD simulation incorporating all the intermolecular and intramolecular interactions, then you will be forced to take a very small delta t, because the delta t will be determined by the highest frequency amplitude, highest so basically the delta T will be dictated by the slowest process in the system, and which would be the bond vibrations. So, we will be spending a lot of time in investigating the bond vibration, whereas we might be interested in looking at the collective properties of the molecules. So, in such a cases what we can do is we can ignore certain time scale processes which are happening at a very, very short time scales. We will treat them differently, whereas the slow modes or the slow processes like the nuclear motion, the torsional motion or the rotational motion can be explicitly considered. So, what I mean by that is, if you consider, so let me plot this molecule here. So, now if you look at this particular N-butane, we have in the full description you will have the bond potential for all the 3 bonds. Similarly, you will have the bond angle potential for the angle bending, and also about this particular bond the molecule can also rotate in 2 planes, and that is what relates to the torsional potential. So, in such a case what we can do is, if the bond vibrations are quite fast, then we can treat these bonds as rigid bonds. So, in a molecular system, bonds can be treated as rigid constraints. So, that means the bond can in this particular example the molecules will be allowed to undergo angle bending. It can also undergo torsional, but if you look at one particular bond, it is always fixed at a particular equilibrium length. So, we do not have to explicitly describe bond potential. The bond potential we defined before is not required anymore, because we are going to always keep the bond at L equal to L naught. So, this is going to be a constraint we are going to impose. This is the constraint we want to impose. So, now when you do this constraint, then we have to see how to do MD simulations with certain constraints like this. If you consider, for example, water, okay, I can describe or demonstrate the application of constraint dynamics using water as an example. So, we will consider a water molecule, and so we have this oxygen and hydrogen. So, we will call this is atom 1, this is atom 2, and this is atom 3. So, in this case we will keep this OH bond fixed, or we keep this OH bond length as a rigid constraint. So, bond length is fixed. So, once the bond length is fixed, this molecule can still undergo fluctuation in the bond angle. It can also rotate, it can also translate. All these other descriptions are untouched. We are basically imposing only 2 constraints for the 2 OH bonds, and this OH bond length L will be some constant. Let us say this L12 will be fixed at D12 and L23 is fixed at some D23. Of course, these D12, D23 are actually the same value in this particular example, but if you have a different kind of bond, each of them can be set to a constant value. So, now when you constrain certain variables like this, it affects the number of degrees of freedom in the system. For example, if you do not constrain, if you ask what is the number of degrees of freedom for this water molecules, so you can see this one water molecule has 3 atoms here, and then for each atom we have 6 6 degrees of freedom. So, 3 for the position and 3 for the momentum. So, total degrees of freedom for a water molecule is going to be 18 per water molecule. Right. So, but now when I have this kind of a constraint, let us say I constrain 2 bond lengths. So, then for such a constrained water molecule, the degrees of freedom will be just 18 minus 2, that is 16 per water molecule. Now, which degrees of freedom to constrain depends on the user. When you do an MD simulation, you have to assess yourself which of the processes that are important for the property that you are trying to calculate, and which of the process you can actually ignore, so that you do not have to unnecessarily waste your computational resources. In this particular example, I might be interested in finding equilibrium density of water, or its diffusivity, or its heat capacity, such a property of a collective motion. So, in that such a case, then I am not so much interested in the looking at the dynamics of the bond vibration, because that is not going to be giving any important contributions in the overall property predictions. So, in such a case, you could actually treat some of the unwanted degrees of freedom as constraints. Okay. So, that is the idea. So, now the question is, in the last slide we saw that for a general description of all the intermolecular and intramolecular forces, you can set up the equation of motion and then apply some finite difference method and solve. Now, we have come to a different situation where we specify, apart from the potential energy, we specify certain constraint also. So, now given that you have certain constraint, how the equation of motion changes and how the finite difference method have to be applied is something that we want to discuss today. So, in order to see this, how the equation of motion changes when there is a constraint or when there are many constraints, we have to again go back to the way we derived the equation of motion, which is using Hamiltonian principle. So, if you recollect, we have discussed this Hamiltonian principle is this: an integral I of the Lagrangian between time t1 and t2, such that this I is minimum, this integral is minimum. And then we also define this L of q dot q is nothing but the kinetic energy minus the total energy. So, when you apply this Hamiltonian principle, we said you could derive the equation of motion this is the equation of motion. And then if you take a kinetic energy and potential energy form which are decoupled from each other, that means if kinetic energy is only a function of the momenta and the potential energy is only a function of coordinates, then this equation basically turns into Newton's law of motion. So, now for deriving equation of motion in the presence of a constraint, we follow a similar approach. We again start with the Hamiltonian principle, but some changes are being done here. So, we do the same thing T1 to T2, and then we also add whatever number of constraints you have. Let us say there are m number of constraints, and then you multiply this with a factor of lambda times f alpha. So, now we say that this particular quantity is minimum. Now, this is same as Lagrangian like we discussed before. So, here this alpha is an index that goes from 1 to m, and m is the number of constraints. You may have one or many constraints. And then this f alpha here is the constraint equation. So, in our example where we said this OH distance was fixed in the water molecule case, you can think of this F alpha could be something like the distance between the 1 and 2, that is OH distance squared is equal minus the constant value should be equal to 0. So, this is the constraint that we impose for one OH bond. Similarly, you can write for the other one also. Let me write, this is 1 and this is 2. So, what we want is that at any point of time in the simulation, we want the distance between 1 and 2, atom 1 and 2, which is O and H, should be equal to a constant value, which is the equilibrium bond length D12. Similarly, the other OH bond, which is given by R23, that distance should also be equal to a constant value, which is D23. So, now this function here are basically these constraint functions, and for a given system you can write n number of such constraints as much as you want. Now, there is a proportionality constant lambda a, this is known as undetermined Lagrange multipliers. So, basically what we are trying to do is we are trying to minimize subjected to a constraint, and the constraints are given by these equations weighted by certain undetermined Lagrangian factors. So, now we apply this Hamiltonian principle to minimize this, and then when you apply variational principle to see when this is minimized, then you can show that the equation of motion for constraint dynamics comes out to be the following. So, you can see that when you have a constraint, you have an additional term given by this in the equation of motion. So, this is the equation of motion for unconstrained dynamics, this is the equation for the constrained dynamics. The only extra term that we have is this lambda a times dou f by dou q. So, when we try to then write the Lagrangian using kinetic energy minus potential energy, then you can show that this particular term can be written as a additional force coming from the constraints. So, then we will have the constraint dynamics would be mi as before. So, these terms are similar to what we have done before. In addition to that, we also might have a force, additional force G. This is called the constraint force. So, this force, additional force, is required so as to make the constraint satisfied at every time point in the simulations. So, now if you compare, if you write this equation for the water molecule like we discussed before, so you can write for the oxygen atom and hydrogen atom, we can go on write with suffix 1, 2, 3, etc. And similarly M2, this is for oxygen. So, note this, that in this case this constraint basically involves all the atoms here. If you look at this particular water molecule, so this we are considering these two bonds and it affects all the atoms here, G 1, 2, 3, all of them. That is why you see there is an additional force, constraint force, in all the equation of motions for the first hydrogen, oxygen, and the second hydrogen atom as well. So, now if you ask what are these G1 force, you can see that this is basically given by So, I am basically writing this G1 force by comparing what we derived just now here. So, these are the forces. So, here we have two constraints 1 and 2. So, we expand this term for 2 such constraints, and those are the G1s. And similarly, you can write the G2. This is the constraint force acting on the oxygen atom. So, these are the set of constraints. So, now if you look at these equations, we can get the forces from the intermolecular interactions the way we usually do, and mass we know, and then we can integrate this. But only thing is, so let me also write this with some suffix here, because we do not want to confuse with the other force. So, I will put a suffix a superscript C here, because these are the constraint forces, because in this equation these are the conservative forces coming from intermolecular forces, whereas these ones are the constraint forces. So, we put a superscript C here. So, what I am trying to do is I take this constrained MD constrained equation of motion, and then I write the Lagrangian as a function of kinetic energy and potential energy, and then expand these terms in terms of available constraints. In this particular water molecules, we have constrained two OH bonds. So, those are these functions F1 and F2. And the G1, G2, G3, they all depend on the derivative of these constraint forces with respect to R1, which is the position vector for the first hydrogen. And for this G2, we get the derivative with respect to R2, which is the position vector for oxygen. Similarly, for the third G3 involves the positional derivative of the constraint forces with respect to the second hydrogen atoms. So, now we know these functions, but what we do not know is these constants, these Lagrangian multipliers we do not know, and we basically have to determine these Lagrangian multipliers. Once we know these multipliers, then we can get the constraint for G1, G2, G3 that can be supplied here, and then you do the regular integration the way we do. So now what we will do is we will try to get how to get this G1, G2, G3. So first let us do this G1. So this is the so what I am trying to do is I am using this expression and explicitly writing the equation F1c F2c, which is nothing but the R12 square minus D12 square. R12 square is written as the modulus of R1 minus R2 with the vectorial positions here. Similarly, for this F2 which is the you may recollect F2 here is written as R23 square minus R23 square D23 squared, and this R23 square is nothing but the modulus of R2 minus R3 whole squared minus D23 square. So now all we have to do is we have to differentiate this function with respect to R1, similarly differentiate this particular function with respect to R1, and you will see that in this case you get 1 by 2 lambda 1 2 2 times R1 minus R2, and this will be 0, and then you have 1 by 2 lambda 2 3, and if you look at here, none of these terms are a function of R1, these are all function of only R2 and R3, so this is going to be 0. So that means G1, the constraint force for the first hydrogen atom is simply lambda 1 2 times R12, that is it, and this R12 is the scalar variable. Sorry, this is basically a so what you have to do is this is going to be a vector actually, yeah. Similarly, if you write you can take this expression write this F1c F2c and then differentiate with respect to R2, you will see that G2 comes out to be, I will write down the result here, but something I can check. Okay, so so now all these three can be substituted here. So now let us see how to apply our Verlet algorithm for this particular problem. So this is what you would do in the case of unconstrained dynamics. For constrained dynamics, this equation will become, now that we have two kinds of forces, so up to this term is the same, and here we have an additional term, that is delta t square by m times G1 of t, and this G1 should be obtained from this particular expression, and now I can put a suffix I here, so that this applies to all the atoms in this case, where I is equal to 1 or 2 or 3 for all the 3 atoms, 2 hydrogen atoms, 1 oxygen atom. So, now if you see this 3 terms here is basically the update that you do if as if it was a unconstrained dynamics. So, therefore, what we can do is we can write this equation a little bit more briefly. So, what we are writing here is that we are writing this entire term as R I prime, and this is basically the position update without any constraint force, position update without the constraint force. In other words, when you apply Verlet algorithm for unconstrained when you apply the Verlet algorithm for constraint dynamics, you first calculate what would be the position update without applying the constraint. You take that and then you add this additional correction because of constraint force for each of the atoms in the system. So, now you can actually now write it now explicitly for each of the atom here. I am going to write R1 at T plus delta T is R1 prime at T plus delta T plus delta T squared by M1 G1, and similarly for the oxygen, the M1 and M3 are basically the same, but in this case we are keeping it anyway different to make it general. So, now and again we note that G1 is given by lambda 12 R12 and G2 is given by minus lambda 12 R12 plus lambda 23 R23 and G3 is given by minus lambda 23 R23. So, now the since we do not know all these Lagrangian multipliers, we have to obtain them. To obtain them, what we can do is we can use this property that the distance between 1 and 2 at T plus delta T should be equal to at a time t as well, and this should be equal to d12 square. And similarly R23 at T plus delta T, this is the distance between the other OH bonds. So, this is the constraint that we want to impose. So, now that we have obtained an expression for updating time positions, now we have to insist that this particular conditions have to be satisfied by these equations. So, to do that, what we need to do is we have R1 and R2, we can take R1 minus R2 and take the square of the magnitude and then equate that to d12 square. Similarly, now we have another constraint, we have d2 and R2 and R3, we can subtract R2 minus R3 and then take magnitude and take square and equate that to d23 square. When you do that, then you basically have a set of quadratic equations, and that will allow you to solve the Lagrangian multipliers. So, suppose if I write that, so if I take this and I write R12 is equal to R1 minus R2. So, I take this and subtract this, you will see that so I am taking R1 and R2, I am subtracting them and then I am writing what is R12 and that basically becomes R12 prime. This is as if there is no constraint force applied, and then you have this additional 2 terms which are functions of the Lagrangian multipliers lambda 12 and lambda 23. Similarly, you can also write for R23. So, now we have these two R12 and R23, and then we take square of them and then equate that to R12 square. And if you do that, you can see that there are terms which are delta t square, and then if you take, let us say you take this and then square them, you will get so you will get the square of the first term, and then you get the square of this term, and this is going to be of the order of delta 2 to the power 4, and then this will have lambda 12 square, and then if you take the square of this term will also have order of delta t to the power 4, and then you have lambda 23 square. In addition to that, you also have 2 times So, what I have done here is I am taking the square of the magnitude of this particular function, and you will get square of the 3 terms. The first term remains, the second and third term will give the quadratic function of lambdas, but then they will have a prefactor of delta t to the power 4, and then you can actually ignore this thing, because if you remember, even the Verlet algorithm, for positions we ignore delta t to the power 4 terms, higher order terms we ignore anyway. So, if you do that, then we have only lambda linear terms in terms of these undetermined coefficients lambda 12 and lambda 23. So, on the left hand side, this should be equal to d12 square. That is a constraint we want to impose. And then if you look at the right hand side, we know this, because anyway this can be calculated without constraint force, and then we are ignoring these 2 terms, and here delta t is known, m1 m2 is known. We also know what is the unconstrained R12 prime, and then we also know at the current time t what is R12. Okay. And similarly, if you look at this, the only unknowns in this equation are the lambda 12 and lambda 23. All the other terms in these equations are known. Similarly, you can also write for d23 square by taking square of this term, and you will see something very similar. You will have so I just ignore all these higher order terms and retain only the linear terms in Lagrangian multipliers. So, if you see, basically you have 2 equations. So, in this equation also we know this, we know all the terms in this term, only thing we do not know is these constants lambda 12 and lambda 3. So, essentially you have 2 equations and 2 unknowns, and you can solve these equations for lambda 1 2 and lambda 2 3. Once you have these lambda 1, so when you solve for the lambda 1 2 and lambda 2 3, then we basically can go back and then update the particle positions using the expression. That is all. So, this is the final step where having found these coefficients lambda 1 2 lambda 2 3, we substitute them in this equation and then finally update the particle positions. So, this basically done in one single step. The first thing is to get the unconstrained positions and then use this constraint equations that we derived here, these set of constraint equations, and then solve for the coefficients lambda 1 to lambda 2 3. Once these coefficients are known, then a final update on the particle position can be done, and from here onwards, if you want to calculate the velocities, you can use again Verlet algorithm to do that.
Sir?
Yeah.
Sir, in the we have mentioned FC constraint, FC, right? F1C, F2C. So for F1C, it is actually square of distance between oxygen and hydrogen at any particular distance minus bond square length, right?
Yeah, yeah. That's right.
It is for one hydrogen and the other is for other hydrogen. So how did you write for oxygen? I did not get that.
No, I am not writing anything for oxygen. All I am saying is that we have this oxygen and hydrogen. So, this is 1, 2, 3. So, this bond length here is given by D12, this bond length is given by D23, and then there is a particle position for hydrogen and oxygen, right, at any point of time. So, that is given by R1 and R2, and this is evolving in time because of various intermolecular forces. So, at any given point of time, if I calculate R12, which is R1 minus R2, and if I take the magnitude of that, should be equal to the bond length, which is D12. So, this is a constraint we want to insist, and you can see that the oxygen atom is actually involved in the OH bond. So, that is why the position of oxygen atom also comes within this constraint force. That is why if you look at this M1, so when we write this equation of motion, we write for all of them. Yeah, if you look at this set of equations, there is a constraint force for hydrogen, oxygen as well as the other hydrogen, because this hydrogen is connected to the two OH bonds. So, the constraint force is something that is required to make this distance always constant. So, that means what happens is this: suppose if you do not have this constraint, what will happen is this bond length will go beyond its bond length. I mean the distance between the atoms O and H will go beyond the bond length. So, we need an additional force to bring it back to the distance that we want, which is the bond length. So, that's how you should understand this.
I have missed in deriving these last equations. Could you please repeat this?
Okay, you understand what we have done here? So, what we have done here is we are writing the particle positions without putting any constraint first. We get a particle update, and then we add the additional acceleration coming because of this constraint force FIC, right. And now we do not know this term right now because this G1, G2, G3 they all depend on this Lagrangian multiplier, we do not know yet. So, we keep them in this equation, we are not updating it, we are just keeping them as such. Now that I know individual a position of the atoms, I can calculate what is the the distance between two species. So, I can for example calculate what is R12. So, this is going to be the distance between the hydrogen and oxygen atom, the first OH bond. For that I am basically calculating R1 minus R2 using this expression. So, when I subtract this minus this, then I get R12 prime T plus delta T. Then you have to subtract these two terms, and then here I am substituting for G1, G2 from these equations. That is why you get these additional terms here. You can see that G1, G2 are now written in terms of lambdas, lambda 1 2 and lambda 2 3. And similarly, we do that for R23 also. This is the other hydrogen bond between this and this. So, the first term will be the difference of these two, which is nothing but R23 prime at T plus delta T, which is a known quantity, and then you have a set of unknown quantity because you are subtracting this minus this after substituting for G2, G3 via these constraint equations. Then you get these additional equations. So, then we say that this is basically a vector, this is a vector, and you take the magnitude and square them, and that should be equal to the bond length that we want. Okay, that is the condition we are imposing here, and we use this condition so as to get this undetermined constants lambda 1 2 and lambda 2 3. Okay, so and here so we have this basically you have something like R12 in terms of some 3 components, and here you can write this as a square plus b square plus c square plus 2 a dot b plus 2 a dot c plus 2 b dot c. So, now so if you see this particular R12, the first term, the square of this term is given here, and then we are going to square this term. So, when you square this term, you are going to have delta T to the power 4 order of magnitude, and this is something we can ignore because this is a higher order terms which we usually truncate up to. And then similarly, the third term also has a delta T to the power 4 term. Okay. So, in this, so this cancels, this also dropped, and then we have 2 times a dot b. So, that is 2 times this term multiplied by this term, that is of the order of delta T square, and we keep it. And then similarly, a and c, so that means this and this also remains. But if you look at b dot c, that is the product of these two terms, will again give another delta T to the power 4 term, which again we ignore. Okay. So, we retain only we retain so this term also drops. So, we retain only this a square term, 2 times ab and 2 times ac, those are these terms. First term here, so this is the a square term, this is the 2 times a dot b term, and this is the 2 times b dot c term, sorry, a dot c. And similarly, you do this for the square, the d to 3, because this the square of this term should be equal to the bond length, which is d to 3. And this case also you are going to do the same thing. You see that the first term remains, and then this delta T square terms remain. And if you look at these two equations, only unknowns are the linear coefficients lambda 1 to lambda 2 3. You have 2 unknowns and 2 equations, and from here you can find out what are these Lagrangian multipliers, and once you have those, then you can come back and substitute here and then update in the final step. Is it clear?
Okay, sir. So one last question, sir. Sir, you have calculated degrees of freedom for constraint molecules. Sir, I did not understand how you did that.
Okay. Yeah. So, if you recollect, suppose you have n atoms, okay. For each n atoms, there is this position and then there is momentum, and this has 3 components of position and this also has 3 components of momentum. So, for every one atom there is 6 variable. So, n atom will have 6 n variables, right, or degrees of freedoms. Now, in the case of water, if you think about one water molecule, this basically has 3 atoms. So, 3 times 6 is 18 degrees of freedom. In the unconstrained situation. So, that is what I have written here. And then now if you have 2 such constraints of maintaining 2 bond lengths rigid, then this is going to be the total degrees of freedom is going to be 18 minus 2, that is 16. That's what I was trying to tell.
So if the molecule has 5 bonds, we are constraining all 5 means, then it will be reduced for this.
But then 5 times 6 also you have to go, right? 5 times 6 would be 30.
Okay.
So,
okay, sir.
Yeah.
So we can also do this by not constraining complete all number of bonds.
Yes, you can.
Only one bond constraint and also.
Yeah, you can actually do that, but in this particular example, both of them are same OH bonds, so there is no reason to do one and not do the other one. But in other cases, you might want to do. In fact, for simplicity, I used only 2. I constrain only the 2 bonds, but you can also constrain this angle here. Okay. So, if you want to constrain the angle, what it means is you can think of some fictitious bond between H and H also. So, you can think of another bond which we call D13, which is the bond length of, there is no bond, but actually you can think of some virtual bond length between H and H. So, if you keep this constant, what you are essentially doing is you are also fixing the angle between the OH. In the actual simulation, this is what is being done, and I thought this I will discuss in the next class. So, you have a choice what to constrain and what not to constrain. So, in this particular example what I showed in the class, I am constraining only the 2 OH bonds, and then I am letting this HH, the HH can actually vibrate, the angle can actually open and close, it can be quite flexible. But if you want to keep that also rigid, you can do that, so that you will have a planar triangular molecule where all the 3 bonds OH, HH and the OH, all 3 could be also constrained. So, now you will have an additional constraint here between H and H, then again you have to rework this entire expressions, right, and then you have some additional constraint force, and so the actual constraint dynamics for water molecules actually is done with the constraining all the 3 bonds here actually. So, the short answer is yes, you can constrain 1, you can constrain 2, you can constrain 3, or you can constrain any number you want. It is up to you to decide what is relevant for your simulation.
Okay, sir.